folks, welcome back. This is Joel, and in this video, let's talk IPv6, right? It's going to be pretty much fundamentals, at least in this video, and maybe we might get into complicated stuff in subsequent videos. So the main agenda is going to be, we'll be talking about IPv6 addressing, right? That being said, I think IPv6 becomes way easy if you know IPv4, right? And personally, even I don't use IPv6 on a day-to-day basis, but yeah, if you know your IPv4, this becomes like a cakewalk, right? So I just have pulled up probably the, I pulled up a Wikipedia page on the IPv6 header just to show you, you know, how it kind of resembles your IPv4, right? So if you see here some of the fields, you will find them, or most of the fields are very familiar to you if you know IPv4, right? See, you have the source address, destination address, exactly same as v4. The version field is there, which was also there in v4. I mean, here they're calling it as traffic class, but in v4 it used to be type of service, right? Payload length, I think it was called as total length in case of IPv4. And then you have the next header, hop limit. Hop limit was nothing but time till. So majority of the fields, I think, except the flow label, rest of the fields, majority of the fields are very similar, or the meaning of them is very similar to IPv4, right? A notable omission is, you know, the fields relating to fragmentation are not available in IPv6, because IPv6 technically, you know, at least, I mean, I can't say fragmentation is not supported, or because that statement would be incorrect, but at least from a IPv6, in IPv6 fragmentation is not done by the intermediate nodes, right? So it's completely removed from here. Anyway, so I just wanted to quickly show you a glimpse of the header. Now let's go back to what we'll be doing. So today we'll be configuring IPv6 mainly from an addressing perspective, right? We'll look at various ways of configuring IPv6 addresses. But before that, I'll spend few minutes giving you some kind of, you know, little bit of kind of like a review of IPv6, right? The various concepts, and we'll talk as if it's like a story, right? So we'll try to make it as simple as possible. Okay, cool. So we looked at the header. What else? So let's start with, why do we even need IPv6, right? I think most of you know this answer, because if you pick, let me just grab my whiteboard here. Yeah, that's good. So if you look at v4, what happened in v4? We had 32-bit addresses, right? So this was just 32-bit, which kind of is 2 power 32, which is around 3.4 billion, I believe, right? You just had 3.4 billion addresses, and you know, look at the population now, and everyone has a cell phone, right? Everyone, you know, everyone is using wearable IoT devices, and you know, basically, it's 3.4 billion is nothing, right? So you can't use this, you know, in the current situation, right? But then, as a band-aid, right, they obviously came up with what we call as NAT, right? NAT works beautifully, yes, but then there are some limitations of NAT, or basically some challenges which NAT brings to the table. Yes, it kind of tries to solve the problem of limited IPv4 space, but things like, you know, end-to-end connectivity is kind of lost, right? Or visibility around end-to-end connectivity is lost because of NAT, right? Because at the edge, you're going to translate your internal address to a public address, and then, you know, through the internet, it's going to, you know, the packet is going to go with a new address, and you know, and then, you know, in the reverse direction again, there is a translation. So, you know, the end-to-end connectivity is kind of lost, right? And then there are many other challenges as well, but NAT was supposed to be like a band-aid, right, until we completely move towards IPv6. And then the other important thing is, other cool thing about IPv6 is that it doesn't have broadcast, right? Your v4 had broadcast, right? Now just to spend probably a minute here, why are broadcasts bad, or why do people frown upon broadcasts? So for that, it's a very common question as well. People ask you like in interviews and stuff, right? So take a router, right? What's going to happen when you shoot a broadcast to it, or when you send a broadcast to it, right? Most of the time people are going to tell you that broadcasts are dropped by the router. It's partially correct. I would say broadcasts are not forwarded by the router, right? Because if they were dropped, then, you know, there was a certain older protocol like RIP version 1 and all would not probably work, right? So imagine you're shooting a broadcast, and then you're also shooting a unicast, and you're shooting a multicast to the router. When I say shooting, you're basically sending, right? Now with your unicast and multicast, what really happens is, at the layer 2, you're going to have a unicast, for a unicast packet, you're going to have a MAC address, right? In case of multicast packet as well, you're going to have, at the layer 2, you're going to have a L2 multicast MAC address, right? So as a result, the NIC which is there here, right, the network interface card, which is there on the router, is going to look at that packet, it's going to look at layer 2, and it's going to decide if that packet is destined to that NIC or not, right? And based on that, it's either going to permit it, forward it, drop it, whatever, right? But basically, all of that happens in hardware. That's a key word here, right? So these both, it's going to, it's going to analyze, the router or the NIC is going to analyze these packets in hardware when compared to broadcast. With broadcast, what's going to happen? The layer 2 is completely FF, right? All Fs. So the packet will have to be shot up the OSI model, right? You have the OSI model. So you have layer 1, you have layer 2, layer 3, and so on. So the packet is going to be shot up, and it will reach the layer 3, and then it will be shot up to layer 4, which is like a transport layer, and on that, OSI model or the TCP model, right? My bad. So it's going to be sent up, and that's where the decision is going to be made, right? So the packet, you're going to open the packet and going to look at, okay, does this packet have, maybe is this packet talking to some kind of UDP port, right? Say, for example, UDP port, just like a random port, say 77, right? So if the router finds that, okay, this packet is talking to UDP port 77, and if there is some kind of a service running on that port 77 configured on the router, then the router is going to consume that packet, right, and going to make decision based on it. But then if this is not really talking to any of the ports, then we basically wasted the CPU cycles to analyze that particular packet, right? So that's why broadcast is kind of frowned upon, because it kind of consumes CPU, right? And you can't really analyze the packets in hardware. You have to really send it all the way upwards to your layer 4 and so on to decide if that packet is useful or not, right? So that's why broadcast is frowned upon, and you really don't have broadcast in IPv6, which is a really cool thing, and we'll talk about that more later. But yeah, so these were probably some of the things on the top of my mind with respect to why we need IPv6, right? Let me get rid of that. So now let's probably pick a quick IPv6 address. How does it look? A quick example. Something like, let's pick a global address. So it's going to be 2001 and maybe DB8, right? Always remember, in IPv6, like I said, it's 128-bit. Okay? And each field is going to have 16 bits, right? So let me grab that. So this is 16 bits, right? So each field, and you're going to have 8 of those fields, right? So let's say DB8, and then probably 100, and let's put in a 0, another 0, so we did 4, you need 4 more, right? And then probably, let's say 10, right? So that's a proper IPv6 address, right? Each of these is 16, and we have how many? We've got a total of 8 here, 8 fields. So 16 into 8 is your 128 bits. So that's how you get your 128-bit IPv6 address. Now the common thing you probably would have seen this is, if you're feeling a bit lazy while writing your IPv6 address, you have a cool feature wherein you can group continuous zeros of this sort, right? And you can replace this with colon, right? Double colon, right? So that's just a common thing which I wanted to put it out there, right? So that's important thing. The other thing is, you might ask a question, if I'm doing like a HTTP on this, right? If this is the IP address and I'm talking to, if this is the IP address of a web server, and how do I mention the port? Because let's use a different color here. So if I have to mention the port is generally, say, something like 8080, right? So the port also will involve a semicolon. So you're using semicolon here, you're using semicolon here. How does the browser understand, right? So to avoid confusion, what you can do is, technically, this is not something which, I kind of forget this as well, because it was there in my notes. I just remembered it. What you can do is, you can put in a bracket, right? You can put in a bracket over here like this, and then you can use this format while you have ports, so that you can avoid the confusion, because technically this also can be like an octet, right? So you would get confused. I mean, technically it could be a field. It appears to be a field of IPv6 address, so you could get confused. So you can use brackets of that sort. All right. So let me get rid of that. So we looked at a common IPv6 address, right? And now probably let's look at a couple of things, right? One is what are the types of IPv6 addresses? The first one which comes to my mind is linked local, and the second one is global, right? There's other one which is unique local, which is like your, just like your private address space or your RFC 1918 in case of IPv4, right? So this is sorry, not unicast, right? Unicast, my bad. So I was supposed to say unique. Okay, so this is generally your unique local address is what they call, right? Basically the address which is supposed to be used in a private non-connected network, right? This is a non-routable, like you can't use it on the internet, right? But the most important ones are these two. Now linked local is non-routable, just remember that, right? This is non-routable. This is supposed to be used only in a segment, right? And just probably like a quick example of why you would do this is like, think you have a, I don't know, maybe like a, think of this as a WAN gateway, right? This is a WAN gateway, like a edge device, right? And this is probably like a headquarters, and you have a branch over here, right? These are the WAN edges, and you're connecting these both. Now in IPv4, you really had to use some kind of a, address here. Like there was no other option. I mean, you could do something like IP unnumbered, but 99% of the times you would use a IP subnet. So probably something like /30, right? You would use a /30. You'll have to put in an IP address here. You'll have to put a routable IP address here, and then those addresses are basically /30, which means you'll basically end up wasting 4 addresses for that, right? But technically, if I ask you a question, is it really needed to put in a public IP over here? Because would you ever kind of talk to these IPs, right? I mean, unless you're using some kind of a network monitoring solution, you would technically not want to talk to these IPs, right? Ever, because they are not whatever these IPs are, they are not for some kind of clients, right? They are not printers, or they are not laptops, right? So you would technically not want to talk to them, right? So that's where in IPv6 what we can do is, right, we can kind of use what they call as a linked local addresses, which are only for that particular link, right? So you can use here linked local addresses, right? And they live only inside this link, or in that segment, not just link, right? You can also have a segment, probably put a switch in between, and you have a segment over there. But they are non-routable. They can't escape out of that segment. They just are alive only over there, right? They will allow for these two routers to talk to each other, but that's it. You can't talk to that IP from anywhere else. So that's the main use of linked local. And then you have the global addresses, which are your provided by your IANA, right? That body which gives out your IP addresses and so on. So that's your global addresses, right? Very much similar to your public addresses in your IPv4, I would say. So that's like your address types. And then some people also kind of categorize, when you ask them about addresses, they're going to categorize in 3 different other buckets, right? They call it unicast, and multicast, and the third, kind of like a new thing, probably would have not heard, but it's like Anycast, right? Technically, I would categorize Anycast as a subtype of unicast, because it's nothing very new. I mean, unicast and multicast, I think you guys know by now what they do, and you can go back to my videos on multicast and check out more about multicast and stuff, but I'll not spend more time on that. But let me just spend a few seconds on Anycast, right? So Anycast is generally used in in CDN, or maybe one of the example is Umbrella, right? Cisco Umbrella, just like a cloud delivered firewall and cloud delivered security, right? Or cloud delivered DNS, right? So Anycast is really useful in such scenarios because you're probably going to have, let's imagine this, right? You have an internet over here, right? And maybe here you have some country in US, right? Maybe a US country, and then here you have some country in Asia, maybe India, right? Where I am based out from. So you have say you have a continent over here, you have a continent over here, and you are providing some kind of a service like basically umbrella, right, which is a DNS base. So what you can have is you can have a server here, right? Let's call it as server 1, and you can have another server over here. Let's call it as server 2, right? But both of them are providing the same services, right? So they're providing the same service, which is cloud-based security, cloud-based DNS, cloud-based firewall, whatnot, right? So anyone sitting here, right? Anyone sitting in India wants to use it, or anyone sitting in US wants to use it. They would technically want to use the server which is closest to their country, right? So this guy should get routed to this one, whereas this guy sitting here should get routed to this one, right? So that's the use case of Anycast. So what they do is they go and put an IP address here, let's call it A, and they use the same IP address here as well, right? And by doing so, what happens is, and when they advertise in the routing, what's going to happen is your basic routing kicks in, right? So when this guy tries to reach A, the best path for him will be this one, and he'll get reached to that particular server, whereas someone sitting in US will get redirected to the one which is closest to them, right? So that's where the whole concept of Anycast comes into play. And there are teeny tiny differences between IPv4 Anycast and v6, but that's the general idea of Anycast, right? Again, cool. So that's about everything which I wanted on the top of my mind, but there's one important thing which I want to talk before we get into the whole address assignment space, right? Let's actually try to trace the journey of a IPv6 address, right? Let's try to trace the journey, right? A life of a packet, whatever, right? Now, one important thing you need to understand is, let me just put this statement out there. In v6, right? What do we don't have? ARP. We don't have ARP, right? So let's try to answer this question. So how does really things work? Without ARP, how do you think people are going to talk to each other in IPv6, right? To answer this question, I'm going to give you a quick, let's call it story, right? And we'll introduce a lot of cool things while we talk about this, right? So yeah, let's do that. So let's assume we have this. We have maybe a switch, and you have, clients hanging out of there, right? Let's say you have a laptop. This is my laptop, and then I have a printer, and maybe some other device, probably a badge scanner, or maybe some kind of maybe a sensor or whatnot, right? Some other device, maybe a phone. Let's say a phone, right? All of these are IPv6 enabled, right? Which means my whole network is IPv6 enabled, and these are 3 clients connected, right? How do we get that completely enabled and stuff? We'll talk later, but let's assume for a minute. Now let's also assume that that our clients have got the IPv6 address, right? We'll obviously talk about how it got and all in the subsequent sections, but let's assume for a minute that all the 3 guys, right, they have got an IPv6 address, right? I showed you how IPv6 address looks like, so let's assume that they have gotten it. What happens next, right? I have received my IPv6 address, right? All the clients, all the laptop, printer, phone, all of them have received it. So once I receive, like I said, let's not care about how I got it, but we have got it. Okay. The first thing the client does it using that IPv6 address, it's going to form what we call as this is probably new, probably you're hearing for the first time, or maybe you already know, but this is what it is, right? It is called solicited node multicast. Yeah, it's a mouthful, but very important. Multicast address, right? Solicited node multicast address, right? So what it is going to do is it has received a IPv6 address here, isn't it? So using that IPv6 address, it's going to pick the last 24 bits, right? So let's actually take an example to explain that. Let's take, for example, 2001, maybe let's say I'm just getting very lazy, so I'm gonna put a double colon, which means everything is zeros, and maybe the last two fields are gonna be something like FE29 and maybe 9C5A, right? So this is your IPv6 address. This is a very legitimate, IPv6 address, right? It has 16 fields. Obviously, it has 8 fields, out of which obviously 5 fields are zeros and the rest is this one. So what is a solicited multicast address? So as soon as it gets this IPv6 address, a client has received this, so it's going to form a solicited multicast address. And the solicited multicast address has the format, right? It is, let me use a different color. The format is going to be FF02:1:FF00:104. So this is the format of the solicited multicast. So whenever anything starts with FF in case of IPv6, always remember it's a multicast address. And this is also a multicast address. In fact, it's multicast address with the scope of link local. So it's a link local multicast address, right? But this is your solicited multicast address, and this is how it looks. That's a format, right? Now what this guy is going to do is, this client which has received, right? We are talking about this laptop. It's received an IPv6 address with this one, right? Using this, it is going to form its multicast address, which is nothing but this one. This is the format, but it is going to use what? The last 24 bits. So what are the last 24 bits? You have 16 here plus 8, right? So that's your 24. So your solicited multicast address is going to be what? It's going to be FF02:1:FF, right? Till here it's going to be same, but only after that it's going to change it to 29:9C5A, right? So that's going to be your solicited multicast address. So the solicited multicast address is going to be different for different IPv6 address because it is using the last 24 bits of the IPv6 address. Cool? Great. So let me just get rid of that so that it doesn't confuse more. Okay. Give me 1 second. My pen is hanging for some reason, yeah. Alright, so I couldn't get rid of that, so I just erased everything. But anyway, so what have we done? We have received the IPv6 address. Let me get my pen. Yeah, so we have received the IPv6s, and the client has formed what we call as a solicited multicast node multicast address, right? Let me just get a bit lazy over there. Anyway, so it's done that. Now what does it do? Right, so it has formed the solicited multicast address. Now the device basically sends out what we call as a neighbor discovery message, right? So it will send a ND, neighbor discovery, right? So neighbor discovery is very much synonymous to your ARP, right? So I would say neighbor discovery kind of takes over or does the job of ARP, which was used in IPv4, right? So neighbor discovery is the new thing. What is this neighbor discovery? It's actually not a protocol by itself. It is just a functionality of ICMPv6. Right? So these things might be a little new to you. So you might be confused. Okay, we were using ARP. So what are we doing instead of ARP? So that's where this thing comes into play, right? So we use neighbor discovery, and neighbor discovery is nothing but ICMPv6. We'll probably see some packet captures later to actually see how that packet looks, but neighbor discovery is actually used in case of ARP. But anyway, so let's come back here. So what has happened? We have created our solicited node address, and we are kind of creating what we call as we send a discovery message to what? We send a discovery message, a neighbor discovery message, right? It writes on ICMPv6, but we send it to whom? We send it to this same solicited node, right? Now, why do we do this? We do this because we send it to this node, and we expect on a good day, we expect no one answers, right? Because if someone answers, then it means that someone else also has received the same IPv6 address, and they have generated the same solicited node multicast address, right? And if that person responds, you're in trouble, because that's where duplicate address comes into play, right? So this is a very interesting mechanism, and that's what we call, why we did this is because it's a mechanism in IPv6 and we call it as DAD, duplicate address detection, right? So step number 1, I create my solicited node address, and then step number 2, I send a neighbor discovery to that solicited node address, expecting no one in the segment, kind of answers back, right? Let's assume that DAD has passed, which means, no one else is having the same last 24 bits, right, of the IPv6 address. So as a result, let's assume that it's very rare, right, in a segment where, multiple clients are going to have the same last 24 bits, right? It's super, super rare, right? I mean, I've never seen it ever happen. So yeah, it's super rare. But yeah, technically there is a possibility of it to happen because, generally the last 24 bits are based off the MAC address, and there is a possibility multiple vendors might use the same last 24 bits, but it's super rare, so let's not get into that. I mean, even if it goes to that extent, the DAD will kind of fail, and the client will obviously generate a new IPv6 address, right? But anyway, so let's not get into that. Let's assume that DAD has passed, which means no one else is having the same IPv6 address, right? So once that is done, step number 3 is basically the client, which is the laptop here, is going to be happy that DAD has passed, and it's going to assign that IPv6 address which it has received to the interface, right? And then it'll assign, and what it will also do is it will join this solicited node multicast address, right? It will join, because it's a, what is it? It's a multicast address. Multicast address, you always go and join, right? So it's going to join it, okay? So once it is going to join, what is going to happen next, right? It will no longer send anything to the solicited node. From now on, step number 4, you can say it will start listening. It will start listening to this solicited node multicast address because it has joined it, right? So it will start listening. Why will it listen? Because what if tomorrow a new client came here, right? Say another laptop, say laptop 2, and it got an IPv6 address, and say you're unlucky and someone gave it the same IPv6 address, right? So when it sends, this neighbor discovery, right, to the same solicited node, my laptop here can respond back saying, dude, look, I'm already using it, back off, right? So that's why from now on it will start listening, right, waiting to answer if anyone else is trying to do DAD. Cool. So that's about how the DAD works. Okay, so now what's happening? We are all good. We have received the IPv6 address, we are happy with our address, we have joined the solicited node. Now the only thing is, why do we even need addresses? Because we want to talk to someone else, right? So in this case, let's say we want to talk to a printer, or we want to talk to the IPv phone. How does that work? So that's where the ARP was coming into play, right? And I just already mentioned to you that neighbor discovery is kind of doing the job of ARP, right? But we did not discuss how it is happening, right? So let's talk about that. So here, step number 5, I want to talk to someone. How does that work? Okay, so if I'm talking to someone in the same subnet, right, in IPv4 we used to do ARP, or we used to ARP. If I'm talking to someone in a different subnet, I used to ARP the gateway. Now in my case in IPv6, what do I have? I say I want to talk between the laptop and I want to talk between the IPv phone. What will I have sitting here? I'll know this guy's IPv6 address, right? That's how you can talk to someone, right? You need to have their address. But is that enough? No. If I have the IPv6 address, that's not enough. I need to know their L2 address as well. Only then I can form that frame and I can, send it, right? And that's where ARP was coming into play. But I already told you ARP is not there here, right? So what do we do is, we'll go back to using this cool solicited node. That's why I kept on saying this guy has a lot of significance in IPv6, right? So what we do, I want to talk to, say, this address, right, IPv6 of the IPv phone. But using this IPv6 address, I know the IPv6 address of the IP phone, but using this, can I form the solicited node of this address? Yes, I can, because I showed you the format earlier. You just need to take the last 24 bits of this one, right, last 24 bits, and then use it with the solicited node format, right? So I can create the solicited node address for this IPv6, right? So that's what we do. We create the solicited node multicast address for that phone, right, the IP phone which I want to talk to. right? And then I send a neighbor discovery message to this one. Next is I send a neighbor discovery, but what? To this guy, to this solicited node multicast address. Now when I do that, he's gonna get it. The phone is gonna get that address, get that solicitation message, and is gonna respond with is gonna give me a response, right, to that neighbor discovery, and that response will have the MAC address of the phone, right? So that's how it really works, right? The ARP, you see how we did this without using ARP, we were able to kind of do the resolution, the IPv6 to MAC address, right? So we knew the IPv6 address of the phone. We sent a we obviously sent a neighbor discovery to that solicited node, and the phone would have joined this solicited node, right? Because that is its solicited node MAC address, right? So it would have joined it. So it's going to respond to my neighbor discovery, and it's going in the response it's going to send the multicast. It's going to send the MAC address. All right, so I think this is a good time to kind of double click on that whole broadcast stuff, right? Now in ARP, normally we used to do broadcast, right? The ARP packet used to get broadcasted in the segment, and everyone used to get it, and everyone used to process it. That was a complete proper broadcast, packet. Bump traffic, right? People used to call it, right? Bump traffic. But in case of this, in case of IPv6, that broadcast is really not happening, right? Why though? Let's try to analyze that. So when you send this, the very first thing, right? When you send this neighbor discovery, let me use a different color. So when you're sending this neighbor discovery, you're sending it to this solicited node multicast address, right? And this solicited node multicast address is nothing but a typical, when you look at the packet, right? You're gonna have the here. This is the source. This is the source IPv6 address. The destination IPv6 address will be this one, solicited node multicast address. But this is IPv6, so this is layer 3. In the layer 2, what is going to happen? The layer 2, you're going to have the source MAC address, and the destination MAC address will be nothing but the MAC address of this solicited node MAC address, right? Because remember in our multicast lessons we learned every multicast address, every multicast layer 3 address is going to have a corresponding multicast layer 2 address as well, right? So this will literally be nothing but layer 2 solicited node multicast address, right? Basically it's going to be a layer 2 MAC address of this one, right? There's obviously, you can get into the whole depth of how that whole conversion happens and what is the mapping and stuff, but let's not get into that for a minute. Take my word on it. Just like your L3 solicited node, there will be a L2 solicited node MAC address as well, right? So for a minute, let's assume that this switch doesn't have multicast. Because it doesn't have multicast, or it doesn't support IGMP snooping. Let's assume that. Let's assume it's a very old switch or something and doesn't have multicast. In which case, it wouldn't have received IGMP, join from the phone, right? For this particular multicast address. But still, right? But still, the broadcast won't happen, right? So because there is no multicast happening, what's going to happen is when this ND packet comes from here, right, comes into the switch is going to flood it on all the other ports, right? It's going to flood it, which is totally fine. But what's going to happen is, though it is going to flood it, when it reaches the printer is going to look at this L2, SNM or the solicited node multicast address, and it's going to say, I don't, this is not mine. This is not my solicited node address. So I'm going to drop it, and it's going to drop it in hardware, right? Same, the printer is going to drop it, the second laptop is going to drop it. The only guy who is going to, process it or, who is going to analyze it is basically this guy, IP phone, because IP phone internally would have, as soon as it joined this solicited node multicast address, it would have, also, generated its L2 solicited node multicast address, right? So it will, when it receives a packet on its NIC, it will basically identify it and it will say, yes, this belongs to me, and it is going to process it and send a reply, right? Whereas the rest of the two guys are not even going to send it up to the OSI, upper layers, because it is going to get dropped by the hardware in the layer 2 itself, right? So you understand how you know, we don't have ARP in IPv6. At the same time, we have also eliminated that whole broadcast which used to happen in ARP, right? And we are doing that using this whole concept of solicited node multicast address. All right. So okay, so that's mainly the whole story. I mean, I thought I would do this in 5 minutes, but it took quite some time. So I'm going to pause the video here. So that was the whole story which I wanted to give you, like the background about, you know, right from the point what happens when a client comes online, it gets IP address, and how does it kind of, you know, how does it make sure that duplicate address detection happens, and then how does ARP instead of ARP, you know, how does this whole neighbor discovery work, right? And yeah, and how did we eliminate broadcast in IPv6, right? So all these concepts I just wanted to cover, and I think we are done that. So I'm going to pause the video, and in the next video we will actually get to the configuration, which is basically the address assignment. Okay, cool. Thanks a lot for watching, guys, and yeah, have a good one.